Okay, so when we're talking about alkanes and their reactivity, there typically is not a lot of things that we end up talking about. Alkanes are not things that, like me as a researching organic chemist, we really deal with very often. And the reason is because they have very few reactions, but they have very few reactions because carbon carbon single bonds are very strong and unreactive. So it's really hard to get carbon carbon single bonds to do too much because they just are chill. They like being where they are. So we are only going to learn about one of the two reactions, and it's called the combustion reaction. So in a combustion reaction, we have kind of a general scheme. So that's what we're going to write in this box. We take an alkane and we add oxygen to it, O2. Then that interacts with each other and forms carbon dioxide. So that yields carbon dioxide plus water plus heat. So by combustion reaction, we mean kind of like an explosion. You take an alkane. This is what happens in your car. I guess it's a controlled explosion in your car. We take an alkane, mix it with some oxygen, and provide a heat source, a small heat source to get it started. And then it gives you carbon dioxide and water and a lot of heat or energy. Okay, so this is kind of one of the only reactions we're going to have to learn how to balance in this class. So looking at this, I gave you the same equation kind of blank over and over so that I didn't have to rewrite it for you guys each time. But we need to learn how to balance the equations for combustion. So we're going to look at specifically balancing propane. So unbalanced, we write our unbalanced reactions. So using our format from above, we have our alkane, oxygen yielding carbon dioxide, water, and heat. Okay, then our first step is to balance our carbons. So we see over here in the first half of the equation, we have 3 carbons, but over here we only have 1. So we need to put a coefficient of 3 in front of CO2 to make those balanced. I'm going to go ahead, you guys don't have to rewrite the equation like this every time, but because I did rewrite it to show you guys these steps, I'm going to go ahead and pull down this 3 for the rest of these equations. The next step is to balance our number of hydrogens. So over here we have 8 hydrogens, and on the right side we only have 2. So what coefficient do we need to put in front of water to make it so that both have the same number? So if I multiply H2O by 4, it gives me 8 hydrogens. Therefore, now we're even. I'm going to again carry that number down. And then the oxygens is kind of the hardest part. So on this side of the equation, we have 2 oxygens. However, over here, we have to take into account the coefficients that we found out for the carbons and hydrogens. So here we have 6 oxygens, 3 times 2, and with the water, we have 4. So we have 10 oxygens in the products. So we need to make sure we have 10 oxygens in the starting materials. So in order to have 10, I need to put a 5 in front of O2. So down here is now my balanced chemical equation. And you can double check all of these numbers to make sure that they're right too. Let's do a practice one. Take a moment, do it on your own, and then we'll do it together. So first we need to start with our general chemical equation for the combustion of gasoline, so octane. C8H18 plus plus O2 yields CO2 plus H2O plus heat. Okay, so our first step, let's check, make sure we match colors from above. Okay, Our first step is to balance the number of carbons. Over here we have 8 carbons. Over here we only have 1, so we want it to be 8, so let's put an 8 in front there. Step 2 is to balance our number of hydrogens. We have 18 over here, only 2 on this side, so we need to multiply it by 9 to get there, 18 and 18. And then the tricky step are oxygens. We have 2 over here. Associated with carbon dioxide, we have 16. Associated with water, we have 9. Uh-oh. That means we have 25 oxygens, which is not a good number for us because that means we need 12 and a half oxygens to balance our chemical equation. So that just means that we have to rewrite this. Let's multiply every coefficient by 2 so that we don't have any any non-integers in our chemical equation. So we have C8H18. I'm going to put the coefficients in a minute. O2, CO2 plus H2O plus heat. So let's double everything. Let's put a 2 in front of the number of carbons. Let's double 12 and a half. So now we have 25 oxygens. We need to double 8 to 16. And lastly, double 9 to 18. And you can go through and double check all of these numbers, but here's our answer. Awesome. So our last topic that I want to talk to you guys about is the dangers associated with combustion. So I kind of mentioned that combustion is really a controlled explosion most of the time. When we use it for good purposes, it's a controlled explosion. Even like, I love bonfires. The carbons in the wood that you're burning, that's a combustion reaction. You are burning something and producing energy, producing fire. However, that could be dangerous if it's not controlled. For example, I know I was pretty young when this happened, and so I'm not sure if you guys remember it. However, in 2010, there was an explosion or combustion reaction that went out of control on board the semi-submersible mobile offshore drilling unit named the Deepwater Horizon. This resulted in the largest marine oil spill in petroleum industry history. So there were 210 million gallons of oil spilled. So over here, this is what the oil rig looked like. And a sudden explosion and fire from the combustion of the alkanes that they were pulling out from the seabed caused the massive explosion. There was a combustion reaction, it started a fire, and it just kept going because it had more and more fuel to burn. This caused a lot of animals to die. There's a whole layer of oil above the entire Gulf of Mexico, and it was years and years and years to clean this up. Even when I was an undergraduate, there were still technologies being developed to better clean up oil spills in oceans. So this is kind of an example of this is oil sitting on the beaches in Louisiana. And then this is also pictures of them using combustion, so just burning the oil off of the top of the ocean to try and help get rid of it. So there's a lot of really good things that have come out of combustion, but we also have to be really careful about combustion reactions as well.